To solve this, let's first think about what we need. In order to do resolution, we're using this equation. Let's just put this up at the top for now, because we'll need it for part 2. For part 1, we want to draw the total signal chromatogram. And the first example, this is really straightforward because there's really not much in the way of overlap, the way these peaks are drawn, or the way they would be in real life if they were Gaussians. For example 2, we do have some overlap that gives us something that looks more like this. So already we can start to see some significant differences between scenario A and B in terms of what the final signal looks like when we combine these two peaks into a single total signal chromatogram. Now, where would you get two peaks like we're getting in part B? Where would we get a green peak and a purple peak? Well, this could be if we have two different fluorescence signals where we're exciting at one wavelength, but we have a fluorophore that excites a little bit left shifted than another one. Or it could be where we're looking at two different wavelengths for Raman excitation, or perhaps we're looking at a tandem separation method where we're going into a mass spectrometer and then we've got two different M over Z's that we're looking at. But a vast majority of our life will be looking at this total signal chromatogram, and so it's very important to understand how these things work. So for the second part here, how do we calculate resolution for each scenario? Well, we need to understand what are the various parameters that we plug into our resolution equation. Let's start off with the retention times A and B. So this equation is shifted, it's reversed of how we have drawn it in the past, and that's because these subscripts honestly don't matter. It's simply where we put them on our peaks. So for retention time A, we know that that has to be bigger than retention time B because resolution can't be less than 0. So let's define these terms on our two chromatograms. For scenario A, we're looking at the center of our peak, which is here. So this would be TRA because it's bigger than the center of our other peak, which would then be TRB. Let's do that for the B scenario. Should be very straightforward again. The center of our peak, it's about 2, TRB, and the center of our other peak, which is about 3. So I didn't do the perfect job drawing these, but hopefully you understand. Now, for the widths here, we will just define them as the full width at the base. So that's this width for width A. Hang on, let me get that right. There we go. And the full width for B. We can do the same for our other separation. And by looking at what these numbers are, where the widths are equal to 2, 4 minus 2, and our retention times, we can get pretty easily from the plot. We can come in here and calculate the final resolution. Now, by doing out this calculation, we learn that whenever we get full baseline separation, that's where we get resolution 1. And so what you'll usually see defined as full baseline resolution is a resolution of 1 or greater. Now, whenever you're dealing with true Gaussian peaks, the overlap here at the baseline is still somewhat significant, even at a resolution of 1. And so you might see it listed in various places as baseline separation is resolution of 1.1 or greater, or 1.15 or greater. Now, that's getting into the category of semantics, and I don't really want to argue with the rest of the separation community right now. That's an ongoing discussion. So we're going to just define it as about 1 for this class, because that's an important, easy to remember and easy to derive relationship relating to the baseline resolution. But on the other hand, at the other limit, we're looking at a resolution of 0.5. And that's basically where we can't even tell that we've got two peaks anymore. Remember when we draw out our total separation here, our total signal chromatogram, we get one large peak, and it's very hard to discern that there were even two peaks under that peak with this resolution of 0.5. Anything less than 0.5 can't be calculated. So, what's the deal? If you've got a resolution of 1 or greater, you don't really need to improve your separation anymore. You're already about as good as it can get. If you're at a resolution of less than 0.5, you can't really calculate it, even if you think you can. The reason for this is because you can't truly identify the components that are contributing to the total signal chromatogram unless you have the fortunate situation of having two different fluorophores or two different ions in your chromatogram.